Hey, what's up? It's your old pal, Mr. Cook, and we're going to work through the rest of this review. Did a video going through the first two problems. Now let's go through the next two, number 3 and number 4. So with number 3, we have a rectangular area, 10,000 meters squared. It's got to be enclosed in a fence. One side of the fence has high security fencing, and it costs $10 per meter. The remaining 3 sides are going to be low cost, $6 per meter fencing. What are the dimensions of the rectangle, which will minimize the cost of the fencing? Okay, so what we're going to do is draw a diagram, obviously, because we got a rectangle. Now, one of the sides is going to be like a premium fencing, so we'll like mark that as something special, like that one. Then the other 3 sides, are just going to be typical fencing. So let's name our dimensions. So if it's a rectangle, opposite sides are the same. And it says that the area is going to be fixed at 10,000 meters squared. So, I know that the area formula for a rectangle, that's going to be X and Y multiplied together. And it's fixed at 10,000. So it looks like this thing is going to be our constraint. Next, so we're trying to minimize the amount of money that we spend. So we got to figure out how to get, the amount of money that we're going to spend on the fencing. Well, so a cost function would look something like this. The cost is going to be dependent on how much fencing that you use, which is, dependent on the lengths that you have for the fences. So we're going to add up all these sides and we're going to include the cost on them. And then that'll figure into the total cost of the fence. So we have one side that's, normal fencing, X. So it's going to be $6 for every meter that you have for X. We'll just say 6X. And then another side over here that's going to be the same thing, another 6X. And then we have another side over here that's going to be a length of Y that's also $6 per meter. So $6 times Y. And then the last one is the expensive fencing, this last side over here, which is $10. So we're going to do 10 Ys. So if we add all that stuff together, combine like terms, we get, looks like 12 X's. And then 6 and 10 gives us 16. So 16 Ys. And that's our cost function. So in an optimization problem, we follow the same criteria as before, or the same steps, we get, 2 functions. One's a constraint. One's going to be like a function that we're trying to maximize or minimize. And then what we do is we get it in terms of one variable if we can, if it's in multiple variables, that is. And then take the derivative, find the critical numbers, and all that stuff, okay? So that's what we're going to do here. I need to get one of these variables in terms of the other. So I'm going to get Y all by itself. So Y is equal to 10,000 over X. And then I'm going to replace the Y in here with X so I can get the cost function in terms of just X. So I get 12X plus 16 times 10,000 over X. Then I, maybe make it look a little bit nicer. 16 times 10,000, that's going to be, what is that? 160,000, right? Yeah, I think so. 160,000 over X. And then, I got to take the derivative of this cost function. So maybe I'll change it one more time. You see that 160,000 over X? That might be a little bit easy, not easy, but challenging to take a derivative or to see what steps you need to take with the derivative. So it's really a good idea whenever you have a variable in the denominator to just convert it into an exponent power. So when I have X by itself in the denominator, that's the same as saying X to the negative first. So I'll rewrite this as 160,000 X to the negative first. Now the derivative is going to be really easy, and the rest of the steps should be pretty easy as well. So if I take the derivative of the cost function, C prime, that's going to be equal to, 12X becomes just a 12. And then with the power rule, the negative 1 goes out front, so I get a negative 160,000. And then I get X to the negative second now, because I subtract 1 from the exponent power. Okay, I'm going to make this look, like a normal function for me. I'm going to get rid of that negative exponent by bringing it down into the denominator. So now this is going to become 160,000 over X squared. And now I start talking about the critical numbers, because when you want a minimum value or a maximum value over an endpoint, you want to look at endpoints, and you also want to look at critical numbers. So the way that I find critical numbers from this function C prime, there are 2 ways that I can do it. One is by setting it equal to 0. The other one is by taking the the cost function and finding any X values that give me some math restrictions, like it breaks a math rule or something. And I actually see one of those right away, because if I'm dividing by X squared, what X value am I not allowed to use? That's right, I can't use 0. So, that's one of my critical numbers, X equals 0. And next, the other way that I can get critical numbers is by taking the cost function, setting it equal to 0. So that's what I'm going to do. I'm going to take the cost function and set it equal to 0. 12 minus 160,000 over x squared. And let's remember that we have a critical number of 0 already. Let's find some other ones. So how would you solve this one? Well, we can add the 160,000 to both sides. So 160,000 over x squared, make that positive now, is equal to 12. And then multiply both sides by 12, by x squared. So I get 160,000 is equal to 12 x squared. Divide by 12, so you get x squared is equal to, let's use our calculator for that one. Goodness gracious. Okay, 160,000 divided by 12. It gives me 13,333.333. And then I take the square root of both sides. So x is equal to about plus or minus the square root of that stuff. All right. Now let's talk about these critical numbers that I have accumulated. 0, and then also the square root of 13,333.333, and negative square root of 13,333.333. So 2 of those don't make any sense in this problem, right? Because if I'm talking about dimensions of a fence, I can't make the x value 0, right? Because I can't have a side of a fence be 0. And then also I can't have a negative number plugged in for x. So I can get rid of both of those critical numbers, or just kind of not really think about them much. So I'm going to exclude that one and also that one. So that's my lone critical number that I'm going to consider. And now let's use the first derivative test to figure out if this is indeed going to be a minimum that we get. Okay, so for the first derivative test, we just draw a little number line here. And then, 0 is kind of like a cutoff value for us because we're not going to have any side length less than 0. So I'm just going to start my number line there and then go through the square root of 13,333.333. And then I've got 2 intervals to look at, 0 and that square root. And then that square root and every number above it, right? So let's see what happens when I plug in selective numbers. Like if I were to pick a number between, say 0 and the square root of 13,333.333, maybe the number that I would pick is 1, to represent that interval, because if I plug in 1 over here in the denominator, that just is a 1, right? 1 squared is just 1. So that becomes 12 minus 160,000, which would just be some negative number. So that means that on the left-hand side of this critical number, it's going to be decreasing. And then for numbers that are greater than square root of 133,000.333 and infinity, I'd probably pick I'd think about my next couple steps. And whatever number that I pick here, I'm going to square it. And what would be an awesome number to pick in between the square root of 13,333.333 and infinity? The number that I would choose to put in there is the square root of 160,000, because if I square it, then I get 160,000, and that's what I'll do. So I'll plug in that number, and 160,000 over 160,000 is going to be 1, and 12 minus 1 is going to be a positive number. So it's going to be increasing over here on the right hand side. So if it goes from decreasing to increasing, this is definitely going to be a minimum value, and that allows me to find all the dimensions that I want, because I know that my x value is going to be equal to the square root of 13,333.333, and I don't remember what the units were. Meters of fencing. And then also the y value is going to be, let's see here. Whatever the x value is, I got to plug in over here and divide it into 10,000. So whatever this number ends up being, 10,000 over the square root of 13,333.333. And then that's also going to be a value in meters. And then it says does it say to find the dimensions that will minimize the cost, or does it tell me to find the minimum cost? It says find the dimensions. So there we go. Those are my dimensions that I would use. And if I had my calculator, maybe I'd find out what those actual numbers are and round them 3 decimal places. I don't know. Kind of depends on how much time I have. Okay, now let's take a look at number 4. So number 4 says, a poster is to be produced from a piece of paper with a total paper area of 180 inches squared. And it has 1-inch margins at the bottom and the sides and a 2-inch margin at the very top. What should the dimensions of the paper be to give the largest printed area? Okay, so yeah, let's work on this one. Let's take a look. So we're going to make a piece of paper right here. And this piece of paper, it has dimensions of X and Y. And I know that its area is always going to be 180, I think it was inches squared, right? Yeah, inches squared. So I can relate the area to these two dimensions. Area is equal to X times Y. And so that means that, 180 is going to be equal to X times Y. This is my constraint. So what am I trying to maximize? I'm trying to maximize the area of the printable space. So the printable space is going to be the space on the paper that is outside of the margins, or I guess rather inside of the margins. So in the description, it said that there's 1 inch margins, on the sides. So I got to go in by an inch here and in by an inch here. And then also I have an inch margin at the bottom, so like right there. And then a 2-inch margin at the top, so like right there. So that means that my printable area looks something like this, okay? It's got an inch, of margins on either side, and then also an inch of margins at the bottom, and then 2 inches of margins at the top, okay? So that's like my printable area, this area right here. And that's what I'm trying to maximize on this piece of paper. So how do I find out the maximum area, or just the area of that printable area? The printable space. So here's what I'm going to do. I'm going to write a new variable. It's called the area of the printable space. So I'll call it A with a subscript of P. Kind of fitting for an AP class, don't you think? So like AP is going to be my area of the printable space. And the way that I'm going to find it is this. It's still a rectangle. My drawing kind of sucks, so it doesn't quite look like a rectangle, but it is. So how do I find those dimensions? Well, here's the other thing. I want to get those dimensions in terms of X and Y. So it's actually like not that bad to do because like the base of this rectangle, let me get maybe a different color so I can highlight it. Where's the little marker thing? There it is. So like this length right over here, I can get that in terms of X because I know that this length is X here, but I can take away these two 1-inch margins to get this length, at the bottom of the printable space. So the area the area is going to be dependent on the base, which is going to be X minus 1 and 2 inch margins, so minus 2 times the height. And the height is going to be the same as this dimension here, Y, minus this one, this 2-inch margin and this 1-inch margin down here. So it's going to be Y minus 3. Okay, so now I'm going to use the constraint over here. And then I'm going to plug it into the Y value over here. And can you already see it? I've got, a function that's it'll be in terms of one variable, X. And I'm just going to repeat the same steps that I did with the previous problem, right? Okay, so let's work with this. Let's get the constraint in terms of one variable. So, let's do that. So we've got, actually my constraint's down here, isn't it? 180 is equal to X times Y. Okay, so I'm going to get Y in terms of X. So here we go. Ready? Y is going to be equal to 180 over X. So then when I replace it in here, A subscript P is going to be equal to X minus 2 times parentheses, and then it'll be 180 over X minus 3. Now, I've got to take the derivative and all that kind of stuff. But what I'm going to do first is like FOIL this. Now, it's because I'm thinking a little bit ahead. I've got to, take the derivative of this thing, and it might be easier just to FOIL it out and try to work with the power rule for a lot of this stuff instead of product rule. So that's what I'm going to do. I'm going to FOIL all this stuff and multiply the x's in there. So what do I get? AP is equal to x times 180 over x is just going to be 180. X times negative 3 is a negative 3x. And then if I distribute in the negative 2 here, I get negative 2 times 180 over x, which is a negative 360 over x. And then negative 2 times negative 3 is a positive 6. All right, let's combine like terms. 180 plus 6 is 186. There we go. And then I'm going to rewrite that negative 360 over x. I'm going to rewrite it as 360 times x to the negative first. Now it's just power rule. This stuff's going to be pretty easy. So I get the derivative. So a prime is going to be equal to the derivative of a constant is just nothing, so 0. And then negative 3x, its derivative is just negative 3. The derivative of negative 360 x to the negative first is going to be a positive 360 x to the negative second. And I'll probably rewrite this a little bit. I'll probably put the x squared in the denominator. There we we go. And maybe I'd even move that negative over the other side there. So like 360 over x squared and then minus 3. There we go. That's a little bit better. Okay, now my goal is to find the critical numbers and do all that stuff, right? So the critical numbers. One way that I can find it is by taking the area equation and setting it equal to 0, the derivative of the area equation. The other way is to take the area derivative and find what x values give me like a DNE kind of thing, right? Well, I already see one of them, right? Area x cannot be equal to 0 because that divides by 0. So that gives me another x value. This is going to be, a no-go though, because I'm not going to be able to find a printable surface with a width of 0. That doesn't make any sense. But we'll just keep it up there as kind of humorous, okay? Next, well, let's do the part where we set the derivative equal to 0 and let's solve. So if we set 0 equal to 360 over x squared minus 3. If I add 3 to both sides, that'll give me 3 is equal to 360 over x squared. Then if I cross multiply, 3x squared is equal to 360. Then if I divide by 3, I get x squared is equal to 120. And that means that x is going to be equal to plus or minus the square root of 120. Okay, so those are my two other critical numbers, square root of 120 and negative square root of 120. But again, when I put my number line together for this derivative, I'm not going to factor in the negative number. And 0 is really just kind of a placeholder. I don't really need it. I'm not going to use it as a value, but I know that nothing's going to be lower than 0. So the only critical number that I really got to consider is the square root of 120. I'm pretty confident that's the one that's going to give me this maximum printable area. But let's, show that it's true. So let's pick a number between 0 and square root of 120 to plug into this derivative equation right down here, okay? All right, so let's see. Maybe a good number to use between 0 and square root of 120 would be 1, because, if I plug in 1 down there, 1 squared is just 1. 360 over 1 is 360, and 360 minus 3 is, some positive number. So that means it's going to be, like, increasing there, so up. And then a number that's greater than square root of 120, that would be probably a good idea to plug in there, I'm guessing would be the square root of 360, because then if I square it, it's just 360, and 360 over 360 is 1. 1 minus 3 is going to be a negative number, so it's going to be decreasing on the right-hand side. So sure enough, that gives us a maximum at that point. And that, it's a windfall from there. We know exactly what we're going to be plugging in for all the other stuff. So the dimensions that we're going to use are x equals the square root of 120, and I forget the units. Oh, it's inches. So inches. And then y is going to be, well, how do I get y? I use the constraint over here, and it looks like it's going to be 180 over the square root of 120 inches for the other dimensions. So there we go. That gives us the maximum, and those are the dimensions that we would need. Okay, that's it for this video. 3 and 5. Oh wait, was it 3 and 4? Yeah, 3 and 4. So all right, that's it for this one. I'll see you in the next one. Bye-bye.